our second ever computer science colloquium. Our colloquium series we started this summer, and the intent is to have kind of short little meetings like this where faculty and even students might talk about particular things or technologies or approaches to solving problems with programming and other computing tools. Something that might not necessarily fit in a class, but something that might be broadly interesting to lots of folks. Professor Schuster was kind enough to run our first colloquium about a month ago. And if you missed that one and want to know, it's about kind of 2D game programming, sort of a little roguelike simulation. That's up on our YouTube channel. You can check that out. And then today he volunteered again to talk about cellular automata, some in the context of games, but sort of more broadly about the tools and how we might use them. So with that, Professor Schuster, why don't you take it away?
All right, thank you, Charlie. So today it's going to be about fluid dynamics, but a very simple fluid dynamic model using cellular automata. Let's see. All right, so first, you're going to need a few tools if you want to follow along. So I'm going to be using Eclipse. We're going to do this in Java. I know that for the CS folks that are here, you've used Eclipse, you've used Java. For some visualization, we're going to use JavaFX. That should be pretty common for everyone who's done some CA stuff as well. Dave is currently posting the GitHub project link. So this is the same as last time. There's a starter project in there, there's this presentation, and there is the sort of finished Eclipse project as well. So I have the link on the slide, and the link is in chat if you want to go grab that. To follow along or just look at as we go, or to actually sort of code with me as well, since I will be doing some live coding stuff too. As far as the setup goes, you will need to create a JavaFX project. Now, of course, depending on your version of Java, the version of JavaFX you're using, the operating system you're using, you may not be able to just directly import the project from GitHub. You will need at least Java 1.8 because we use a few of the features from that in here. But otherwise, if for some reason you can't import it, just create a new JavaFX project, just a blank one, and take the files and bring them right in. There's only 2 files that you have to worry about. There is some starter code. We don't quite have time to code everything, but the majority of the meat that we have to do this simulation will be coded live right here by us. So there's a few empty functions in the main class, and then I have an already written sort of grid element class. And really this just represents the squares that we're going to draw to the screen for the visualization. So I'll talk about that class and sort of show you what it looks like. It will be very familiar to those of you who have had me for CS2. It's sort of the same style of sort of class along with JavaFX shapes and stuff that you've seen me use in the past. So it should be familiar for those who have had me before. All right, so while you sort of get set up and go get the GitHub project and potentially create a JavaFX project and all that, I just want to talk a little bit about cellular automata. So in my CS1 and CS2 classes, and also potentially a little bit in the parallel programming class that I teach as well, I use cellular automata to show up certain concepts. In CS1 and CS2, that's typically arrays. We talk about 1D and 2D arrays in this sort of CA context. CA itself typically just represents a simulation. So you have a whole bunch of cells, and they each have specific states, and the simulation runs based on a particular set of rules. So sort of the best known CA is what's known as Conway's game of life. So a lot of you have probably seen this before. You may have coded it yourself as well. It's relatively straightforward to code in Java. That's what I typically show it in CS1 and CS2. So John Conway developed the CA in 1970, and there's a lot of actually cool interviews of him talking about it and sort of how he came up with it, and that I think they first did it on paper to see if it was useful, and then they actually did some programming with it. So there is some really cool resources that have him talking about it. The game itself isn't really a game. It's kind of a 0-player game. You set up the initial board, which oftentimes you can just set up randomly, and then you let the simulation run. and you get some really cool situations happening within the board. You get oscillating cells, and you get cells that create this sort of motion across the screen. So you get some really cool complex behaviors from some relatively simple rules. If you have me for CS1 and CS2, you've sort of seen this stuff, but I think it's worth, if you've never seen Conway's Game of Life before, I think it is worth going out there and taking a look at it and just seeing what cool configurations happen even when starting from a random initial board. But this sort of mathematical curiosity isn't the only thing that CA is sort of useful for. So lots of games use CA to simulate physical processes. So if you've played a game like Terraria, for instance, this is a 2D game. You sort of dig around the world, fight bosses, all that kind of stuff. But they have liquid in this world. And the liquid uses cellular automata to look mostly realistic. Same thing with games like Oxygen Not Included. That has liquid and it has gases, and it simulates those things in the game world using CA. If you played Noita before, the entire game world, every pixel in that game world is CA. So every single grain of sand, every single liquid, every single gas is simulated with CA. Now, these are all sort of side profile view games, but that sort of doesn't stop us from doing top-down stuff as well, which is what we're going to focus on today for the particular model we're talking about. The reason why this is useful is because CA can be efficiently calculated, especially on multi-core processors. And when you don't need something that is 100% physically realistic, then CA gives you something that is close enough to look good. And as long as it looks good, the player's not going to care whether it's solved using partial differential equations or simple rules in CA. It just has to look good enough. So that's sort of where CA can sit. It sits between this sort of realism versus sort of performance. And when you're talking about video games, performance is what you want. You want the most performance possible while looking as good as it possibly can. So this is why CA oftentimes is used in video games. All right, so at a fundamental level, CA is a model, and it contains a system of cells. These cells have some characteristics. They live on a grid. That grid can be 1D, it can be 2D, it can be 3D, it can be higher dimension if you want to, although displaying a higher dimensional grid onto a screen can be a little bit difficult. Today, we're going to focus on 2 dimensions. So similar to the games that I mentioned above, this will be a 2D simulation. Each cell has some kind of state. States are usually finite. You usually have a fixed number of them, something like 0 or 1, which could represent things like on, off, dead, alive, something like that. Our fluid dynamics model today is going to be 16 states, but it'll be relatively easy to sort of work these states out. We're not going to have tons and tons of code that we try to look at each individual state. We're going to have simple rules that make this much, much easier for us to deal with 16 states. Each cell also has a neighborhood. So this is the region around each cell that changes the behavior. And you can define the neighborhood in any way you want to. Some neighborhoods are more complicated, some are simpler. It just depends on the simulation you're actually trying to run. So as an example, here we have a 2D grid. Each grid cell has a state on or off. If we look at an individual cell, so the cell that's sort of circled here, if we look at an individual cell, then we could say our neighborhood is all the adjacent cells. So that includes the diagonal in this case. So our neighborhood is 8 cells, plus our center cell gives a total of 9. So this is one way to look at a cellular automata, and this is essentially the way that you look at Conway's Game of Life. 2 states, you pick a cell, it has 8 cells around it, plus itself is a neighborhood. That neighborhood is called the Moore neighborhood. So the center cell plus the 8 directly adjacent ones. For our fluid model, we're actually going to choose an even simpler neighborhood. This is the von Neumann neighborhood. It's the center cell plus only the cardinal directions. So we're only going to deal with up, left, right, and down. Those are our only cells that we care about. in addition to the center cell. So we don't care about the diagonal ones. This simplifies our life actually quite a bit, which will be quite nice for the coding that we're going to have to do. So von Neumann neighborhood, 2D grid. The model that we're going to actually use, how we're going to simulate this top-down fluid, is known as the HPP model. The HPP are the last names of the guys that came up with this in the 70s. This was the first CA fluid dynamic simulation. It has a few characteristics. You have particles in your grid, and they move along a lattice. In other words, they move along the grid. So particles, they move left, right, up, and down on your grid. That's their sort of allowed motion. Each cell in my grid contains 4 nodes. So this is where it gets a little bit more complicated, but it's what allows us to actually simulate a fluid in a mostly decent way. Each of those nodes within a cell is either occupied or unoccupied. And I have a picture of this coming up on the next slide. The actual grid updates occur in 2 steps. There's a collision step. So this is in each cell, the particles, however they're arranged, they do some sort of collision math. And then there's the propagation. The particles within the cell then move to new cells. They move to the adjacent cells. Some particles will move up, some will move down, left, right, wherever the particles happen to be. So it's a 2-step process: collision, propagation. So that's how this is set up. Collision is only within the cell. Propagation has to move things to adjacent cells. So the picture looks like this. Each cell, each of our sort of grid locations, contains 4 nodes. The nodes directly correspond to the cardinal directions. So I have a node that represents the up direction, one with left, right, and down. Unoccupied nodes here in the picture are just unfilled circles, and an occupied node would be a filled circle. So that's the visualization. You could sort of imagine taking a bunch of these cells and lining them up in a 2D grid. That's a visualization of this of the simulation. We're going to use some math in here and a little bit of code that you may have never used before. You may have never even seen it used before. You don't have to do it the way that I'm going to show, but it actually saves on memory. So the node occupation itself could be represented with a single bit. Remember, a bit is just a 1 or a 0. So I could say this set of 4 nodes is 0, 0, 0, 1. It takes 4 bits to represent my nodes. That means the entire cell can be represented, well, by 4 bits, but we don't usually think of bits as sort of separate things in our programming language. We think of bytes. That's sort of the smallest unit that we regularly work with, is a byte. So we can store the entire cell in a single byte. A byte is 8 bits. So 4 of those bits can represent the occupation. Now, because we're going to represent it this way, we're going to use some bitwise calculations, some bitwise operators. These are things that, again, you may not have seen before, but we'll sort of go through them and use them in a few places to help us out. So bitwise calculations look like this. The 3 specific ones that we're going to use are a bitwise AND, a bitwise OR, and then the shifts. So the left shift and the right shift. So 3 different types of operators. You can sort of look through the binary example. The shifts are relatively easy to understand. It's just taking some bits and literally shifting them left or right. The AND and the OR are a little bit more complicated. You sort of got to look at what's going on, but they're similar to your regular sort of logical AND and OR as well. So we'll talk about them when we get to some of the programming of them. So we're going to use these operators to manipulate the bits that represent our cell. I'm going to label it this way. So we have up is A, left is B, right is C, and down is D. So this particular cell with its 4 nodes would be represented in my code as a single byte that looks like this. The leftmost 4 bits, we don't worry about. We don't even need to think about them. The rightmost 4 bits are going to be A, B, C, and D. So this particular cell has a 1 for D and a 0 for the rest. So this would be 0001. We're going to use this knowledge later to help us shift some bits around and determine what these cells look like above and below us, and to the left and right in our von Neumann neighborhood. Now, again, you don't necessarily have to do it this way. You could use a class or like an object for each individual cell and have A, B, C, and D be integers and all of that. That's perfectly a perfectly fine way to do it. That what this way does for us is it reduces the amount of memory that we're using per cell, and it should also be, for the most part, faster. These bitwise operations tend to be very fast. Instead of binary, I'm going to use hexadecimal in the code. It means less typing and less chances for mistake in terms of, as compared to like typing binary. So something like 0x5c. So the 0x means this is a hexadecimal number. The 5c would represent the first four bits in the first number and the last 4 bits in the second number. So it makes it relatively easy to view something as sort of a binary perspective without actually writing out the ones and zeros. So we'll use hexadecimal in a couple of places. It's not going to be all over the place. We're not going to have a bunch of hexadecimal code and a bunch of bitwise operators acting on it. We're just going to use it in a couple places. Specifically, the propagation step it becomes very useful. All right, so I'm going to go into the code. I have a couple slides in here that there's not a lot of context to them. This is just the setup. So this is just getting an initial grid. So first I want to talk about the grid element class. There's not a lot in there. It's just meant to give us the ability to actually draw some small squares on the screen for our actual graphics at the end. And then setting each of those grid points to some value, to a random value. So that's sort of what this does. So I'll talk about it as we go through and code it up. So I'm going to hop over to Eclipse. There's 2 files here. And if you have everything imported correctly, it should give you a blank window to start with. The blank window is, I think it's 384 pixels by 384, so it will be a square window that we're using. And if we take a look at main, I do have some variables and some arrays and stuff set up already. The thing that I want to point out with these initial variables is I am using a byte type. So this represents a single byte, so 8 bits. So that's how I'm actually going to do this. You could use ints for this as well, but typically an int represents 4 bytes. So we'd have a whole bunch of zeros if we were doing our bitwise operation. So I'm just going to use a single byte. And again, if you've never used bytes before, it's just a regular type. Its value is just a much smaller range than a regular int. The grid element class is related to our graphics. So again, if you've had me for CS1 or CS2, this should be very familiar. If not, it just contains a little bit of information. It contains a reference to a rectangle that we're going to change color based on how many particles are in the particular cell. It has a little info about the size of the particle or the size of the rectangle. It's just 1 pixel by 1 pixel. It'll know its own X and Y location, and it'll know its current occupation. In other words, how many particles are in that cell. There's a little bit of setup with the constructor. There's a way to get the graphic, and there's a function that sets the occupation. This just sets the colors. So if there are 0 particles in this cell, then the color is going to be yellow. So we'll have a yellow pixel in our image. If there's 1 particle, it's a green yellow. So we sort of go from yellow to blue. So yellow to green to blue. So up to 4 particles then is going to be blue. And then if something went wrong, then it'll be pink. So hopefully we don't see any pink pixels when we run this. So there's not a lot here. There doesn't have to be a lot here. It's just meant for the graphics itself. So back into main. The first thing that I do in start is create a grid pane. So if you've messed around with JavaFX and you've used a grid pane before, what we're about to do is going to be pretty familiar. So we're going to set up this grid pane with 384 by 384 of my grid element objects. And when we change our data, when we actually do the simulation, we will update the occupation in those cells to change the color. Underlying all of this, however, is the actual data itself. So the actual simulation happens on a 2D byte array, not using the cells, not using the grid element, not using the graphics piece of it. So the graphics will just update, the simulation will happen sort of behind the scenes. All right, so what I'm going to do first is I'm going to create a grid element array. So it's going to be a 2D array. I'm going to call it grid. You can sort of think of this as my graphics grid. So this will be a new grid element. And I've created a static variable for this, so we're going to use size for the size of this. And it does assume square. If you want something that's going to be rectangular for your domain, you'd have to mess around with the code a little bit more than what we're going to do today. Then I'm going to loop over all of it, all of this. So I'm going to add all of these grid element objects to my grid pane. So this is just getting the graphics set up. This doesn't have anything to do with the actual simulation model itself. So we'll start with I equals 0, I less than size, I plus plus, and the same thing for our other dimensions. So we're going to have a j equals 0, j less than size, j plus plus. Then we're going to make sure that our grid, so our grid array at ij, actually has a new grid element. So I'm going to create the object. And the only thing that goes into the constructor here is the position, the ij position. So we know, so the element itself knows exactly where it is located in the grid. Now this doesn't do anything to the graphics. I need to add to my grid pane. So I'm going to say root, that's my grid pane, dot add. So we're going to add a node. And the node we're going to add is grid ij dot get graphic. So we're going to add the graphic associated with that object to the grid pane. So now whenever I update that graphics color, it'll change in the grid pane. And the location is in the ij location. So this sets up my rectangles into the grid pane so that when I run the program, it'll display a bunch of colors depending on the occupation. So if I go back to the grid element, depending on the color it was switched to, I'll get a whole bunch of different colors depending on the occupation. So that sets up the actual grid pane. Now we need to set up the actual values for these individual cells. So we're going to select a random occupation, essentially a random state for all of the cells, and we'll make sure that works. So we'll need another set of for loops. We're going to loop through every pixel again. Now you could combine these together. You could combine these loops, but I want to make this sort of very clear as to the different steps. So I have I less than size, I plus plus, and the same thing again, but for j. Going over our two dimensions. And we're going to make a random value. So I'm going to make a random byte value. I'm just going to call it value. And we're going to use rand dot next int and next int. And I'm going to have this be 13. Now, we'll talk a little bit about why this is 13 later. I've already created the rand variable up here at the top. It's just a new random. I made it static, so so it would already be here ready for us. So this is the one we're using. It's just your regular random number generation in Java. Now notice we have an error here. This is an int. We're trying to save it as a byte, so we need to do a cast. So if you remember your sort of casting rules and when you need to cast and when you don't, going from an int to a byte, we do need to have a cast. 13 here is related to the actual byte values. So again, we'll talk about that a little bit later. For the boundaries, so when I equals 0, actually I'll just say when we're at a boundary, just set value to 0. The boundaries are going to have no particles in them. And that's for a very specific reason once we get to the collision and the propagation. So we'll say if I equals 0 or j equals 0 or I equals size minus 1, or j equals size minus 1. Then we're just going to say value is 0. I don't want any particles in my boundary regions. Then we'll just say data, ij. This is our actual grid. This is our actual simulation grid. Data ij equals value. So data is the actual simulated grid. So it's the thing we're actually going to be running through the simulation. The grid is just used again for the graphics. But I need to do set occupation, and I'll set it with, I have a sort of a helper function here that we're going to use to do this called getBits, and this is going to set value. So it's going to get how many bits are within the value and set the occupation to that. So there's a little bit of hand waviness here. All getBits actually does, and it's just down here. It just grabs a value from a particular array I've already set up. So you may want to look into that a little bit more about how I determine what that actually means, but it all comes back to those 4 rightmost bits in each byte that we're using. So at this stage, we've created our grid that contains our graphics piece. We've gone through and created some random values and put them into our simulated grid, so our simulated data, and updated the occupation, so the color of all of the rectangles in our actual grid. So with these 2 pieces, this should run, let's see here. This should start in a second, hopefully. Yeah, right here. There we go. It gives us, for the most part, a not very interesting looking graphic, but we're going to add a little bit more to this. You can sort of tell if you squint and look close around the edges, it's all yellow. Otherwise, we sort of have a sort of a greenish yellow up to sort of a bluish green in here for all of these different locations. So there's a lot of different pixels in here with a lot of different particles. And remember, the color of each of these represents the number of particles at that particular location, at that particular cell, which represents a pixel for us. So it's not going to be very useful at the moment, but we're going to add a little bit more. So I'm going to go back to the slides. And the next slide down, it's got a couple of things. We will write the setup collision in just a moment, but I want to do this one first. Set up a high density region. So we're going to talk physically about what this means after we set it up and actually look at it when it's running. So you can see that I do sort of an I equals 50 to 150, J equals 50 to 150, and I specifically set the data to be 15. And then I do the set occupation again. So we're going to look and see what that means. So back over to the code. Yeah, let's do that. So we're going to have 4. I equals, we'll do 50 to I less than 150. I plus plus. And we'll do the same thing for J. So J equals 50. J equals, or J less than 150. Remember what our I and J represent. They represent our grid. If our grid is 384 by 384, then 50 to 150 in both dimensions means that we're going to be putting something in the sort of upper left of our actual sort of graphics. So I'm going to say data ij equals 15. We're going to talk about exactly what this 15 means in just a second. And then we want to do the same line, and I'm just going to copy it from up here. The same grid line right here, grid ij, set occupation, get bits. But instead of using value, I'll just grab the data ij again. You could just put 15 in here as well, because that's what the data is. But hopefully this makes a little more sense. So if we save this and run it, we'll see something a little bit different. So just take a moment. It does have to run through everything, and it's been a little bit slow for me. Yep. So here is the high density region we just added. So you might be wondering, why am I calling this a high density region? Remember what the colors mean. They're the number of particles within the particular pixel on our image. So if there's no particles in a particular pixel, then that's very low density. There's no particles there. If there's one particle, it's still low density. If there's 4 particles, that's high density. That's what we did in this region. This is the high density region. And you can think about that in terms of binary. 15 in binary is what? Well, if we think about a single byte, it's all zeros on the leftmost bits, and it's all ones on the rightmost bit, because this represents 1, 2, 4, 8. If you add these up, if we have a 1 in each place, this is 15, which means we have a particle in A, B, C, and D. So 4 particles in every one of the pixels in this blue square. So it's a high density region. Now, physically, what does that mean? What does a high density region mean actually physically? If you've ever used like a wavetable before, where you have like a sort of thin sheet of water along a table, and then you dropped like a big droplet in, that's exactly what this is. We have a very thin little bit of water in this area, a thin bit of liquid, and then we put a big drop in. Now, it's a square drop. It's not very realistic, but we put a gigantic sort of drop of water in. So we have a high density region of water. And what do you expect to happen in sort of real life if you take a smooth sheet, a thin, smooth sheet of water, and add a big sort of gulp to it? You expect to see waves. And that's exactly what we're going to see after we're done today. And that's what you would hope to see from a simulation, from a fluid dynamics simulation. All right, the last thing that I'm going to throw in here is the other thing that we had on the slide. And I think on the slide I had it, and I guess I'll put it where I had it before. I had something called setup collision. This is going to do a little bit of setup for us. Let's see. Spell that. Oh, yeah, set up collision. This is just an empty function at the moment. So it is down here, right here, setup collision. So I do have a little bit of comments and stuff in here, but we are going to set this up momentarily. For now, just remember where we're at. Created all the graphics for our grid. Set up the initial grid, including our array that we're going to use to modify the simulation, and then put in a high density region to act like a whole bunch of water in one particular area in our simulation, or a whole bunch of fluid. This is all for the setup. We actually just need to write a few functions and mess around with our event handler, and then we've got a simulation. So back to the slides. Let's talk about collision. HPP uses only one type of collision. All the other collisions just pass through each other. So here we have a before and after cell. It only uses head-on collisions. So if you have 2 particles coming into each other and you run the collide function, at the end of the collision, these 2 particles will have moved 90 degrees and will be moving away from each other. That's the only collision that we have in the HPP model. However, it is rotationally symmetric. So you could swap the before and after here, and it would work correctly as well. So if it's head on, either up, down, or left, right, head on, it will rotate 90 degrees. The particles will rotate 90 degrees, and they'll head it off in that direction. So a left, right, head on collision will end up, down. An up, down, head on collision will end up going left, right. And that's it. It's as simple as that for the collisions. And the cool thing is, it'll give us some nice waves. Again, all the other configurations, they just pass through each other. So let me show you one of those. Here's a 3-particle, and I'm going to use sort of air quotes here, a 3-particle collision. This isn't really physically realistic. If I have 2 particles head on and a 3rd particle coming in as well, you would expect them to go off at potentially wild angles. But they don't. They pass through. The 2 particles up and down, they don't collide. They just continue sort of moving on up and down. The 3rd particle, in this case, coming from the right, it will just continue on to the left. As far as from one of the questions in the chat, as far as gravity goes, we're considering this to be a top-down simulation. So I know like a lot of games and stuff use use side profile. In that case, you would want to make sure that you have some sort of gravity sort of taken into account. But as far as a top-down perspective goes, we won't have to worry about it. All right, so this may not be physically realistic, but it preserves total momentum. So this is one of those sort of physicsy things. Those of you who have had me before know that I have done physics for a long time, did a lot of physics professionally. So it is something you have to worry about. When it comes to a fluid simulation, you do need to preserve certain quantities, things like particle number and stuff like that. And you can look up all the reasons why and how you do that in more complex situations. But here, momentum is the most important part. And so here, total momentum is conserved in this type of quote unquote collision. So that is something that we do have to be aware of. So to represent the collision, it's not a whole bunch of code. We're going to create a lookup table. What this means is that you have sort of a cell representing the lookup. When I send in a cell that looks like this, so the sort of only the occupied one is the down direction, then this lookup is going to give me the cell that represents the up direction. Because this is what happens with the collision. If I have a cell that represents the right direction, then it'll give me a cell that represents the left direction. Because this is what happens in the collision. They just pass right through. Down here at the bottom, the one I put in here, this is one of the actual collisions. We have a left-right head-on collision. At the end of that, when I send this through the lookup, it's going to give me an up-down collision. This is super easy to program. And it's what's going to be in the setup collision function. My caveat here is this is not the best way to write this, but it gives me a chance to show you what happens with the binary. So remember, our node structure is like this for those rightmost 4 bits, A, B, C, D. In decimal, they would be 8, 4, 2, and 1. And then in binary, of course, you would have the 4 bits. So for example, for 0, that should be pretty obvious. If there's no particles after a collision, you're going to have no particles. But let's take a look at lookup 1. Well, what is 1 in binary? It's this, 0, 0, 0, 1 for those rightmost 4 bits. Well, what does that represent in our cell? That represents a D. That's a D in our cell. That's a down particle, a particle in the down position. So after the collision, where does that particle go? It goes to the up location, which means it's going to be over here. It's going to go from a 1 here to a 1 here. What is that in decimal? That's an 8. A 1 in the A position is an 8. So that's how this works. A particle in the 2 position is a C. A C goes to a B. So a 2 would go to a 4. That's how we use the lookup, because we will send in the decimal value for our cell as the index to the lookup to get what happens to the collision. So you can sort of work your way through all of these. I've put a few of them, a few of the binary versions of them, and in the final, the sort of full project code that has everything written already, you'll see a few more of these as well. The first actual collision that you see here is number 6, because 6 is a B and a C. So that's a head-on collision. After the collision, you get 9. A 9 is an A and a D. So that's how this lookup works. And it's super nice. There's only 16 possible configurations, so you don't have to write some gigantic array, and it makes our collision code very, very simple. So I'm going to code this up right now. I'll probably sort of do a bunch of copying and pasting and then making sure stuff looks right to make this sort of relatively quick. But you can code this up in sort of any way you want to. This was just one of the simple ways to be able to show some of the binary that's actually happening here, and sort of why these values, why does 3 go to 12 and 5 go to 10 and 6 go to 9 and all that. So let's go ahead and do that. Let's go over to Eclipse, and we'll go down to the setup collision. And I actually do have it next to me here as well, so I might just take that in. Let's do that. Just so I don't have to spend too much time writing it out. So here I have a whole bunch of the binary ones down to 15. 15 is all ones, which there's not really a collision from that. It just stays all ones, for example. So that's our setup collision, getting that lookup ready to go. all 16 possibilities for the lookup. Then we're going to write the collision code. So this is that intra-cell collision, the collision that happens where we use the lookup table. And the nice thing about the lookup table is that it's relatively simple. But we do have to, or the collision code itself is relatively simple. But we do have to think about the boundary. And this is why I set the boundaries to 0. So the first and last row and column are only going to act as boundaries to our simulation. So when a collision happens, you can think of it as just bouncing right back. So if you have a down particle and it hits a boundary or it's in a boundary a cell, you can think of it just sort of bouncing off the middle of the cell. So after a collision, it would just stay right where it was. A particle in D before a collision would just be in D after the collision. So we can do that very simply. This is the full collision code. I've been a little bit more explicit here. We don't actually need the if-else. We can sort of leave that off and make this a little simpler. But the full collision code here is actually pretty simple. And then after that, the last piece is the propagation itself. So let's go code the collision, and I will talk about it as I go. So first thing we need to do to collide is we need to loop through every single cell. So we'll do I equals 0, I less than size, I plus plus. And then j equals 0, j less than size, j plus plus. And then we're going to check, are we at a boundary? So if I equals 0 or j equals 0, this is the same if that we wrote before. I equals size minus 1 or j equals size minus 1. We just stay the same. The thing I'm going to put in here is going to be sort of redundant, but hopefully it sort of makes sense. Hopefully it helps this make more sense. The data just stays the data if we're at a boundary. Otherwise, we use the lookup. So our new data cell will be the lookup, a lookup array at index data ij. It's worth turning this into an int as well. It's worth doing a cast here. And let's see, my stuff here is being a little bit of a pain for the, so I may have to look and see where we have a problem. Might be something with line endings or something while I'm not getting the highlighting. In any case, this is the collision piece. Relatively simple. Using the lookup, using the current state of the cell as the index for the lookup, and then getting the new state directly from that. All right, so with the collision in place, the last piece of this is the propagation. How do we move these particles from one cell to another? So I've got a picture of that. Each cell looks to the cells around it within the von Neumann neighborhood. So just left, right, up, down to determine what its next state is going to be. So let's say, for instance, that this cell is the current cell we're looking at, the current cell we're updating. So when we look up, the only thing that we're interested in when we look to the cell above us is there a particle in D that's going to move down to A, which is exactly what happens here. Here's our after. I don't really care about any of these ones because they don't affect the cell that I'm currently looking at. All we care about is that D location. And the D turns into an A. So if you look at the binary up here, we've got 0001 for the rightmost 4 bits. And over here, that changes in our cell, in our new cell, to a 1000. So drawing out pictures like this can be helpful to understand how the numbers are changing so that when you code it up, you know how to code it a little better. You have more intuition about the code that you should write. So we're going to use this idea of we only care about the cell, in this case, the D cell. If we're looking to the left, we only care about the C cell, for instance. So each direction, we only care about one particular cell that we're looking for. So we're going to use masks to do this. The masks I've written here in hex, and they're going to represent what we're looking for. So the up mask, for instance, is a 1. That represents D. So when we look up, we're trying to find if there's a D. The mask is going to be used on the actual cell above us. So let's say the cell above us is a 1001. So it has a particle in A and a particle in D. When I use the mask with a bitwise AND operator, what I end up with is 0001. Anywhere where there's 2 ones, if you line these up, anywhere where there's 2 ones, I get a 1. Otherwise, you get a 0. So like I said, I don't care about A, B, or C. So I'll just leave those as 0 and only check for the down. Here, I'm only checking for C. Is there a particle in C here? No, there's not. So I still just have all zeros. This is how we find the particles that we're interested in. Each mask gives us one of the bits. It tells us, is there a particle that I'm concerned with? Is there a particle in D if I'm looking above? Is there a particle in B if I'm looking to the right? And so on. So that's what these masks do. So let's go ahead and put those in. So down here in propagate, we're going to put them in. These are all bytes. And we'll do up mask equals 0x01. This is where we have a little bit of hex. We will have down mask. This is 0x08. We will have left mask, which is 0x02. And we will have the right mask, which is 0x04. And then I have a few variables that I create that'll sort of help us out with actually sort of completing this. So I have an up byte, and I'm just going to set these to 0 to start with. A down byte, a left byte, and a right byte. So those will just be a few helper variables that we're going to use. And this should be an equals here. Yep. So we'll set up those masks. Again, they're just the particles that we're most interested in. This is pretty much the full code for doing the propagation, but I'm not just going to sit here and code it while I talk to you about it. I do have a few slides related to it. So to get our up byte, we're going to do exactly what I mentioned before. We're going to take the cell above us. So this is the one that's above because we have the I+1. And we're going to apply the up mask. So we're going to use the bitwise and the mask that we have. So that's the first piece. We apply the up mask 0x01 to the cell that's above us. Then we do this. This is using a bit shift. Remember what happens after our mask. If there was a cell, and actually I do have this all on the slide here. If there was a cell above us that has a D particle, our up mask would be able to get that D particle out. So let's say we have all zeros for the cell we're looking at. This is the cell that's above us, and we have the mask. So we take the cell above us, and we apply the mask. So what the result is here would just be a single particle in D. Then we do a bit shift, because remember what happens to the D cell. It needs to become an A in our cell. Well, what's the difference between a D and an A? It's just a shift. It's a left shift of 3. If I take this D bit and I move it 3 over, I get an A bit. And that's it. That's a piece of our new cell. So I need to do this in all 4 directions. When I do it in all 4 directions, then I build my full cell together. So all of these this up byte, down byte, left byte, right byte, we combine them all together at the end. And you combine them, in this case, with a bitwise OR. So let's say we end up with this situation. We have the up byte is an A, the down byte is a D, the right byte here is active, and the left byte is just all zeros. Using the bitwise OR will let us combine everything together. So if we have these bits here, anywhere where there is a 1, we get a 1 in the combination. And this becomes our new cell. Now I understand that this can be this potentially can be a little bit complicated thinking about sort of bits and all of this, but if you go through it slowly and think about all of the individual steps, and you take a simple example of just a couple of bits and see how they move with the shifts and how they combine when you use ors and stuff, these ors and these ands, it becomes relatively simple to manipulate these things. If you were to look up the HPP model in other contexts, in like some actual like science papers and stuff, you'll see that folks have turned this into like one equation, one sort of massive equation with a bunch of bitwise operators. I chose not to go that route because it can be very difficult to decipher an equation like that. So hopefully doing sort of a couple steps like this, sort of one after another to create this byte, hopefully that makes some sense, but it could take a little bit of time to sort of unravel everything that is going on there. Yeah, so let's put that in, and then there's sort of one last sort of piece to this, and then we'll basically be there. So I'm going to take actually the for loop from up here. There we go. So we're going to loop through every single cell, and provided that I is not equal to size -1, we're going to do the up byte part. So this is just to make sure that we don't go outside of the boundary. So I'm going to have some ifs in there. We don't want to exceed the boundary of the simulation. So we'll take the up byte, and this is going to equal. We'll have a cast byte. You do need to be very generous with parentheses when using bitwise operators because the order of operations for them is not always intuitive. So we're going to check the up location. We'll do a bitwise and use the up mask. After we have all of that, we're going to do a left shift by 3. So that takes care of the up byte. And then I'm going to take this piece that we just wrote, and I'm going to copy it a few times and then make the changes to it. So we're going to do up, down, left, and right. And I'm going to change the ifs in here as well. So this will be, yeah, sorry, this should be not equal to 0. All of these should be not equal here. Or not equal to size -1, not equal to 0. And this one will deal with j's. J not equal to 0. And j not equal to size -1. And then we'll mess around with the location here. So this will be data -1. And this will have the j -1 and j +1. So these are just a matter of which direction you're looking. So it's relatively straightforward to sort of reason your way through why it's I +1, I -1, and so on. The last piece here that needs to be different is the actual shift itself. So for this piece, we would need a right shift of 3. Here we need just a left shift and a right shift of 1. So we're doing a shift. We look at the mask and we're doing a shift. So this needs the down mask. This needs the left mask. This needs the right mask. I don't recommend doing the copying and pasting like that because it can be very easy to miss something, but it does end up working rather well if you're careful. After we loop through all of them, we loop through after we loop through all of them, we are going to do a sort of one last thing, but we need to set the byte value. So I'm going to create a variable called value, cast it to a byte, and use my bitwise ors on everything. So I'm going to take in up byte, or down byte, or left byte, or right byte. So this combines everything together. So we have essentially our new cell. And then I'm going to take my temp data grid. So we're going to talk about this in just a second about why this is required. And this is going to equal value. And then we're going to update the occupation. So the same sort of thing to update the colors that we did before. So we do set occupation. And the value here, we could put in just value like this, or you can put in temp data ij. All right, we have one more set of loops to do, and then we're finished. The reason why I use this temp data grid is because we need a secondary 2D array. Those of you who have made Game of Life before will sort of have sort of realized why we need to do this, hopefully. We don't want to directly manipulate the data array because we're currently using it to do our calculations. So we need to store the finished value elsewhere. Then once we're done with the new data array, we can do something like this to copy everything back. In a language like C or C++ or Fortran or something, I would just swap pointers. But in order to make this hopefully relatively easy to understand, I'm just going to copy all the data. So everything we have in temp data, we're going to copy into our new data grid, and then that's the thing that we're going to update on the next collision cycle. So I have one more little loop after we finish everything. So after we're done with those loops, we have one more set of these. And this definitely slows stuff down by doing it this way. So like just being able to swap pointers actually ends up being a lot faster. So we have data ij equals temp data ij. And that should be it for the collisions. So we're basically done with all the functions. The only thing left to do is every single 100 milliseconds, and this is just some JavaFX stuff to run things at a particular tick. We need to do the collision. So we're going to call the collision function. And we're going to call the propagation function. The propagation function does take the grid. So we do need to send in the grid in here. So every single 100 milliseconds after the simulation starts, it will apply a collision, and then it will apply the propagation. So as long as I haven't messed anything up here, this should work appropriately. And we're just about out of time, so we're basically there. So right now it's paused. I have some sort of pause stuff in here as well. So as soon as I press, I think it was space bar or something, or maybe not, then it will go. So we got some pink, so it looks like I had made a mistake somewhere. So let me flip over to the, since we're just about out of time, let me flip over to the full finished one here. And we'll run that one to show you what it should look like. I probably missed something that that is on the slides. All right, so here is what we should get in the end. You can see the underlying grid here. You can tell the grid is square based on this. But what you should notice is this high density region is moving outward. We have this wave structure here. All the other particles that were moving up and to the left, they're going to sort of build up in these directions, and then they're also going to have a wave structure coming out. So we get this high density wave, the initial wave, and then we get the waves that come after it from bouncing off the sidewalls. So we have ourselves, it's a rather noisy fluid simulation, but we do have ourselves a fluid simulation where we can represent particle occupation and density. And you can just let this run. This will just keep going. The image that I used in the flyer, if you took a look at the flyer, the image that I used from that was from a video that I had made, this one. And it is the same thing. It's the same exact model, a little bit higher resolution. The reason why everything looks a bit smoother is because oftentimes what you'll do is you'll take a region of pixels, like a 16 by 16 cell region, and you'll just average it. You'll average the occupation. That gives you a much smoother looking simulation. So that's what I've done here in this one. The arrows for this represent the momentum as well. But you can see the same style of simulation here. You can see the same sort of wavefront here from the initial high density region, and then these other waves that were from bouncing off the top and bottom wall. So this is it's just another version. This is one that I programmed in C, so it's a little bit more performant, so I can do higher resolution versions. But the point is, the Java one works exactly the same way. It's exactly the same type of bitwise operation stuff, and graphics-wise, I'm just outputting stuff and plotting it in a different program. So there was something that I missed in here, so I'd have to go back and take a look. But you do have the full completed code that does work. So very last, I'm just going to skip this finishing up one here. You do have a basic HPP model from this. You could add other things, like putting an obstacle in the domain for particles to bounce off of. However, HPP is not actually a very good model. It shows the underlying grid. We saw that. It shows sort of a square underlying grid. And from sort of a technical perspective, it doesn't solve the Navier-Stokes equations in the continuous limit. Better models are things like FHP, which are similar, but actually use a hex grid. So that leads to more possible collisions. And then there's statistical techniques like lattice Boltzmann and stuff. So this was sort of meant to show you sort of the very beginner stuff for sort of a fluid dynamics with CA. You can take this much further. You can mess around with the HPP model. You can try to code an FHP model, which is a little bit more difficult, but gives you more realistic looking fluids. There's lots of cool stuff that you can do with this. And then, of course, figuring out how to apply it into a video game is exactly what folks that made Terraria and Noita and Oxygen Not Included and a whole bunch of other games looked into as well. So there's lots of resources out there for CA and video games. So if that's something you're interested in, take this as a starting place. See if you can fully grasp all the stuff that I've done here, fully understand it, and then apply it to other situations. There's a lot of cool stuff you can do with CA. So that is it. So I hope that was informative for some CA stuff, and hopefully when we have our next colloquia, we will see you there.
That was really great. Thanks, Professor Schuster. I hope everyone enjoyed this. Certainly fascinating. Also nice to have that refresher on bitwise operations and arithmetic. But thank you everyone for coming. If you have any questions, feel free to stick around. We can stick around for a couple of minutes to answer any. Also, if you have any feedback for us, I'd love to hear it. Or if any of you are here and thinking like you have something awesome you would love to share in a future colloquium as a faculty member or as a student, don't hesitate to reach out. Really, these are just about finding ways to share cool things that we might all want to know more about. So if you have any feedback, feel free to send it to me or Professor Schuster or Dave Albanese, and we'll use that in the future. In the meantime, again, thanks everybody and have a wonderful afternoon.